So today we are going to talk about search, everything you always wanted to know about search, but you were afraid to ask. I guess now you can ask. A few words about me. My name is Mallia. I'm currently a PhD fellow at New York University. My research interest is search, in particular efficiency applied to information retrieval, applied to large-scale systems. Those are my contacts. Make sure you guys connect with me. I'm gonna, follow you back on GitHub, LinkedIn, or Twitter. Aren't conferences all about connection, like networking? So let's do that. What are we gonna see today? Today's agenda. We are gonna learn what information retrieval is, and then we are gonna see how a search engine works. What's crawling? How you index your documents, how you perform query processing, then how you rank them, and finally, how you evaluate your final product, your search engine. Then we're going to see a couple of examples, like how image search works, what's alerting. Alerting is another application of a search engine. I think it's pretty interesting. So let's find out first what information retrieval is, how it is defined. So it is about finding materials, typically documents, among like a large collection, a large corpus of unstructured data. And the reason why you want to do that is to satisfy a user need. Typically, a query, something expressed with words, something expressed with tokens. But this definition actually really describes what a search engine was in the late 90s, early 20s. But still works with modern architectures. What's nowadays information retrieval? Just goes beyond what a search engine is. It's definitely more. One example is question answering. If you look for a question, if you ask a question to Google now, you're actually going to get an answer. You don't get any more results. You are not even interested in results. You're just interested in getting your data, getting your information. Second, when you look for something, you're looking for something that is nearby you. Most of the time, you're just looking for an entity, like a restaurant that is close to your place. Or maybe you're looking for a ride, and you want to share it. You want to do a pool. You want to ride share with someone. So you're looking for a similar ride. Isn't this actually searching? Aren't you searching for something? It's all based on the same concept. Image and music retrieval, media retrieval in general. When you upload a picture on Facebook, all the faces are identified, and they are all compared with all your friends and friends of friends' faces in order to do face detection. This happens. Music retrieval, when you're listening to a song and you're interested in the title, what's going on? You're just comparing samples of your song with samples of a catalog of popular songs. And finally, conversational search. Aren't we all interested in looking for stuff, just asking these things without even typing it? All these assistants, all these chatbots are actually performing a search. They're doing like query processing on a knowledge graph, on a knowledge data set. So all these are examples of of how search engine. All these are examples of. All these examples have something in common. They are all based on a basic search technique that was already working 20 years ago. So I think it's pretty interesting to see how a normal, a classic search engine works. So we're going to explore it. So the very first task is crawling, so finding your documents. You want to find among your catalog, among your corpus, every single element, every single entity, every single document, indeed, web page, if it is a web-based collection. So how crawling works? It's pretty simple. It's a very basic idea. And it's all about finding documents starting from a single web page, starting from what is called a seed. Might be multiple web pages, might be one, might be more than one. But the idea is that all the web is connected. It's a graph. So all the web pages are connected. And starting from one, you start exploring concentric circles around these URLs. And it all relies on hyperlinks between pages. If you want to develop a crawler, it's an interesting task. And typically, a crawler is divided in two parts, a crawling system and a crawling application. Crawling system is the very low-level part of the crawler. It has to be simple, and it has to be efficient. You want to fetch web pages fast. You don't want to wait looking for resolving like a host name. You want to build a DNS cache. You want to make it super efficient. And the second part, the crawling application, that part of the crawler is the one that actually implements the policy. Which page do I want to crawl first? How am I going to deal with limiting the load on a specific website? How often does my web pages changes? So the crawling application is the high-level application that is dealing with all these kind of things. You don't want to see a web page multiple times. You don't want to go over the same web page over and over and over again, because it's a waste of resources. So you want to have also a way to find out very quickly if you already visited that document or not. And the way you do it, well, you're storing your web pages, your documents, your collection inside a repository, which is stored on disk. Do you guys think you can actually look it up every single time you want to decide if you have visited already a web page or not, looking it up on a disk-based data structure? I don't think so. The way you do it with Bloom filters. It's a simple data structure. How many of you know about Bloom filters? Raise your hand. Oh, interesting. OK, we're going to see it very quickly, though. So a Bloom filter is a probabilistic data structure that has basically just two operations, insert and exist. Why do we want to use this data structure? Because when you insert an element inside the Bloom filter, you're not actually inserting it. You're just informing the data structure that element is something you have seen already. You don't want to see it again. So whenever I ask for membership, in this case, exist, I just want to know if the element has been inserted or not. I don't care about the element. So all this allows me to build the data structures that fits my main memory, my RAM. I don't store it on disk, and I can still store the entire collection, being able to test membership against this data structure. It's all about trading space for false positive rate. So if you want to make it like super small, you will get more false positive rates. If you can deal with like larger Bloom filters, then you can get like a false positive rate of 10 to the minus 6. I mean, pretty low, like impossible, almost impossible that you get it wrong. So crawling, it's all about deciding what's your policy. If you want to build a crawler, you want to decide when you're crawling pages, do I really want to crawl like this web page first, or I want to go to another page, like something that is more vertical to my application? If you're building LinkedIn, you're more interested in crawling CVs. If you're building, I don't know, a news website, you want to crawl news websites. A news search engine, sorry. If you're building a news search engine, you want to crawl news websites. And then freshness. How often does a web page changes? Some web pages changes basically every minute. Some others, they never change. You want to decide, given a URL, if you want to crawl it now or if you want to crawl it like in 10 iterations or in 20 iterations, so which means in 10 weeks or 20 months. And this is basically a machine learning problem. Based on your previous observations, you want to decide if this website or this URL actually is worth being crawled now. And finally, you want to decide also how much you want to crawl. What are your competitors? Based on your competitors, based on their coverage, you want to decide your coverage. Crawling is expensive. Those are like some open source crawlers. They have been around for a while. I find funny that wget, a Linux tool, can actually implements a crawler. When you're crawling, you want to output something, and this has been standardized. It's called work. It's the web archive format. And it's just a way to concatenate your crawler outputs into a file, wrapping with meta informations. As I said, it's been standardized. If you're curious about it, you should read about it. wget outputs this format, which is super, it's incredible for me that you get this. Indexing. OK, you got your pages, your documents. They are not only HTML documents. They are MP3, they are doc files, spreadsheet, PDFs. How do you parse them? It's a classification problem. You want to decide what parser you want to use based on the content. And then you want to decide in which language this is. Nothing is only in English or in Italian. We have multiple languages. We have to decide which language we want to, for example, start doing tokenization after. So tokenization is the process of splitting a text into tokens. You want to perform a normalization, basically remove punctuation, remove hyphens, do case folding. How do you do this in Asian languages? I don't know. But you have to deal with it. Even if you want to just exclude or basically focus on Italian or English, you got to find out which language is that document first. And then you want to remove stop words. They don't carry any semantic. They carry very little semantic content. So you want to get rid of all the linking words like the, a, and, to. And these are language related. Every language has its own. Stemming, which is the process of bringing into its original root a word. So for example, if you have cool, cooler, and coolest, you want to just truncate everything to cool. And the way you do it is either using dictionaries or an algorithm that identifies specific language cases, morphological variants. And all this is also synonyms. You want to find an equivalence class between, for example, car and automobile. They are the same word in content, so you want to extend your index to be able to consider the two words the same. And all this is pretty interesting stuff. It's all about natural language processing. There is all a field about how you can improve these single tasks one by one. OK, now we got our documents. They have been parsed. They have been tokenized. And we want to build what's called an inverted index. An inverted index is the basic data structure of a search engine. It's a mapping. It's a mapping between words and the document IDs where that word is contained. So let's give it a look. We take first the collection of documents. We give to every single document an ID. And then we take all the distincting terms, and we build what's called a lexicon or a dictionary. So every term now has a position in this dictionary. Codemotion is the term number 1. After that, we build this corresponding with this correspondence, like this mapping between a word. So a term ID number 1, word Codemotion, it's present in document 1 and document 2. Rome is a way more frequent term. It's present in several documents, 1, 2, 3, 4, 6. These lists can be extremely long in a real world search engine. They can contain millions of integers. And they are called posting lists. For this reason, when we have a posting list, so a list of document IDs that are containing a specific term, we gotta split into blocks. Blocks of fixed size, for example. Every block has a skip pointer, so like an additional data structure that allow you to skip to the next block. So why do we do this? The reason is because sometimes we want to traverse a posting list, but we don't want to visit every single element. So we want to be as fast as possible and skip from block to block without even entering the block. What you can do is you can compress now these blocks individually. And why do we need to compress it? Because these lists, as I said, they're like giant lists. They contain millions of integers. Another information that you can store in every single block, I mean, you get metadata, but you can store, for example, frequencies and positions. And they're useful because positions allow you to tell you if a document contains like a specific term like so many times that it's just made out of that term. This is probably like useless or it's spam or something. We will see more about it later. And then the position. Positions is because you want to do proximity search sometimes. You want to look for a specific person, name and surname. You're looking for name out of with a distance to the surname of 3 words, for example. You're not interested in someone that has like, you're not interested in searching like a name and a surname that are like just around the web page because it might refer to someone else. Index maintenance, 3 basic operations, insert, delete, update. Look, this is not easy. It's a static data structure. It's a static data structure, so updating a data structure like this means keeping a buffer, keeping tombstone, and then redoing like the work once every now and then. Then we said that we want to compress these posting lists. And there are some techniques that are pretty cool, in my opinion. One of these is the delta encoding, D-gap encoding. Every list of integers, it's usually in increasing order. And the reason why we do that is just for convenience. This increasing order allows us to do this technique called delta encoding, which is basically subtracting from each element the previous one. And the result is that the final list is made of smaller integers. Why do we want to do this? Because then we are going to use something called variable byte. Verbyte, vbyte is called, it has several names, also used by Google. Protobuffer used these techniques. Several Amazon used these techniques for compressing their stuff. It's used in serialization protocols. It's pretty cool. Let's imagine you want to store the number 3. Why do you store it in uint, for example, so unsigned int 64 bits or 32? There's no reason. 3 can fit easily an 8-bit word. So you can just use 8 bits, right? But how do you know how many bits you're using? So this technique is actually pretty interesting because it uses a continuation bit. So the final representation of a number is composed of a header called continuation bit and a payload. In the payload, you actually put the representation of the number. In this case, 3 is just a couple of 1s and then all zeros. The continuation bit actually tells you if this is the final word that you're going to use to represent that number. So 7 bits to represent the element, and then a continuation bit. If you need more, your continuation bit will be 1. So for under 33, you're going to use 16 bits, and the final representation is given by this 7 bits payload plus the other 7 bits payload. So you read and you say, OK, what's the continuation bit? It's 1. I need to read more. And you read more. And that's how it works. Another interesting one is called P4. A bit less known, but it's still very interesting. So patched frame of reference, look at your entire list, and then says, OK, I need 2 bits for this one, 4 bits for the other one, 5 bits for the other one. But you know what? With 8 bits, I can compress 90% of my list. So let's just use 8 bits to compress most of my elements. And then for the final ones, which are called the exceptions, I'm just going to use the standard way I use normally, so like 32 bits, for example. You end up with basically 4 times 8 bits plus 32 bits representation, which is way less than 5 times 32 or 64 bits. You save a lot of space with these techniques, and there is a lot of research around it. So after that, you want to start doing processing, query processing. You get a query from a user, and you look it up on the inverted index. Then you start processing with Boolean operators. You do intersection, union, or negation. And then finally, you want to re-rank all these results in order to provide the best ones. Re-ranking sometimes involves also machine learning models, and we're going to see a couple of them. And finally, you just presented with snippets, metadata, and additional information. When you perform query processing, there are two main techniques. One is term at a time. The other one is document at a time. Each of them has its own advantages. Term at a time, you process one term first. Then you go to the second term, the third one, so on and so forth. You got to use an accumulator. You have to store intermediate results from one term to the other, additional memory. But it's faster if you have a lot of terms. Document at a time, instead, you open, and I'm quoting this, you open all the posting lists, all the cursors that are going to traverse your posting lists, and then you traverse them simultaneously. You don't need any accumulator, and it can be faster. You can do some optimization. So Boolean retrieval, you get a query. Your query is made of terms and operators, either and or not. Then you look it up on the inverted index, and you will get these posting lists. Usually, you perform intersections first because they are easier and faster. Unions and negations are performed later. This means you need to rewrite your query. Your output will be a list of results, just the documents. This means that you want to score them and find out, according to the user query, which one is the best and which one is the worst. So you want to rank them, and you want to present it to the user. And you probably want to present just a part of it. You don't care about the tail of the result list. So there are several scoring functions that are all term-based, based on the frequency of the terms inside the document, based on some semantic, like language models. They are based on, they are basically learning what's the sequence of terms usually in a common English text, for example. So based on that, you can rank your results. But that's sometimes not enough. I mean, modern search engines, they rank your results based on your preference sometimes. So you got to build a cascade ranking architecture, where your first phase is definitely made of a simple scoring algorithm, a simple and fast scoring algorithm, and then you output, for example, the first 10,000 or 1,000 results. These are too many for your user. You don't want to present a web page with 1,000 results, so you keep re-ranking and re-ranking. And every time you re-rank, you cut it until you get to 10 results, for example, and that's it's going to be the first web page, the first page of results of your search engine. These complex models, they are very expensive. If you think about it, like predicting with machine learning models based on your preferences means they have to extract your preferences at query time based on that query. This can take time. So you want to do it only for a smaller subset. So one of these re-rankers can be based, for example, on a sort of voting system where every page votes for others. This was the idea of PageBrin and Page and Brin. They came out with an algorithm called PageRank. We all know about it, I guess. It's a system that basically says, you know what? If Wikipedia is linking you, you're probably a good guy. I'm going to rank you high. And that was the first version of Google when it came out. And it seems to be pretty successful. Then they came out with other stuff, obviously. As I said, they rank you based on they rank the documents based on your preferences. And this is called learning to rank, a very active research area. There are a few algorithms that are very popular. One of these is LambdaMart, gradient boosting, RankSVM. We know for sure they are used by industrial search engines, like commercial search engines that you can actually use. So they are probably using this techniques. And there are open source implementations. As I said, all you care is building a feature vector such that you can train your model and you can perform predictions on those. This features vector depends only on the query and the document, how the document is related to that specific query. Once you get to this point, I think you care now to see how well you're performing. So you want to evaluate And evaluation can be tough. There are things called basically judgments, relevance judgments, and they can be gathered. I mean, you want to say if a document is relevant to a query or not. Because if the document that is first in your result set is not relevant to that query, you're doing it wrong. And you want to re-rank or learn more. To do so, I mean, you can do it with the click model. A click model is basically you look at the clicks of your user. So if the users are, your user base is like always clicking to the fourth element, the fourth result, probably that one shouldn't be fourth, should be first. And if nobody's clicking to the first one, then you gotta lower it down. Another technique is you get a bunch of engineers with a lot of free time, and then you ask them to judge your documents. But it can be expensive and slow. Some open source libraries in order to perform query evaluation. And these libraries are going to output precision, recall, NDCG, several metrics. Spam. Search engine optimization is a multi-billionaire industry. Everybody's trying to get I. And they're doing it with textual methods or with link-based methods, or people are trying also with machine learning now. How you control spam? Either you do it cooperative with your user base, with your users, asking them to provide you a feedback. You can do it with machine learning. Given a tax, you want to see if that tax has been maliciously modified in order to be ranked high. Or you can just build a better complex ranking functions. So your machine learning algorithm will put the spam at the end, and then you will just cut it off, and you won't present it to the user. So let's see some additional applications. Any search engine needs an autocomplete feature. How many of you know how to do an autocomplete feature? Again, how would you do it?
Using, for example, like query database or using Elasticsearch.
Right, but how do they do it?
With an Ajax code.
With what?
Ajax code.
Well, you need a data structure below, like inside your engine. And this data structure is typically called a prefix search data structure, like a tree or a trie, depending on how you like to call it. And one of the most famous implementation is called the radix tree. You can perform prefix search on a radix tree, and then based on values, you can re-rank these results. If you notice, these results are not lexically ordered. They're actually ordered based on previous users' query. Seems that many people search just for Codemotion. Some others search for Codemotion Amsterdam. But Codemotion Amsterdam 2019 is the fourth one here. So you have to mine your query log. You look at your query, and then you mine it, and then you insert into these data structures, and then you can finally get the autocomplete results. And this is how it looks like. Alerts. Have you ever used alerts, guys? Anybody? Google Alerts? What do you search on? What do you store in Google Alerts?
Typical query that you want.
Right. But what kind of what terms do you store? You personally? Science, physics. OK, cool. I personally store my name and surname. I want to see if someone is talking about me. How do you do that? This is basically sometimes referred as reverse query. You got a stream of documents that go through Google. Google crawls continuously. If something with my name and surname gets out there, I want to know. And I want to be the first one to know. So you want to do searching over streams of documents. It's the reverse problem if you think about it. You're storing your queries now. Your queries get indexed. And then whenever a new document comes in, so a stream of documents here, whenever a document comes in, it gets transformed into a query. And this query is used to find out what are the people, who is asking for specific things. So you want to match a user with a document now. Once you find this matching, You just propagate this matching, and you notify the user. There are just 2 implementations that I'm aware of. This is a very interesting topic. I know that several companies are interested in this. So if you want to come up with a nice tool on GitHub, this is an idea. Image search. We said that that Facebook, whenever you upload the picture and there are faces in it, is gonna search for is gonna do a similarity search among all the other faces that it has inside its database, in order to find all the similar ones, such that they can do, matching. So in this picture, there's your friend. I know because I can find the similarity that is very close with another picture that I have stored in my database. The way it works is different from what we have seen so far, and I just wanted to show you because I find it very interesting. So it's based on k nearest neighbor or approximate nearest neighbor. The idea is that whenever you crawl, so your images get converted into feature vectors. These featured vectors are a representation on a multi-dimensional space, a latent space sometimes preferred. And the way you get it is through a convolutional neural network. So deep learning. Are you guys familiar with deep learning? Awesome. So once you get this representation, you can just project it into a space. And if a user comes in with a new query, it's going to provide you basically an image. You're looking for similar images. Again, gets converted into a vector. And now I can query it for similarity using a k nearest neighbor algorithm. So you will find all the similar ones. There are several implementations. As I said, all these implementations are by Spotify, Facebook, Microsoft, and then there is another open source implementation from another guy. I think this rings a bell. It means that probably they are very interested in this stuff. They are using it. All this stuff also runs on GPUs if you're interested in doing it faster. And then I want to conclude with some open source search engines that are available out there. We range from enterprise level, like Apache Solr or Elasticsearch, as you said. We have Redis Search, which is a module for Redis. You build everything in memory. This is fast, guys. Vespa used to be, it was released by Yahoo. And then we have some newer implementation like in Go, Rust, like trending languages. And finally, some academic implementation that are used in academia basically to find out new algorithms. And I'm personally building my own web search engine. I mean, not web search, just search engine. I'm building it with other people, other cool guys. If you're interested, you should definitely follow this repository. We accept pull requests. Get involved. And finally, when you want to experiment a bit, when you think you have something cool that you can try, these are common standard data sets that you can use. Common crawl corpus, it's a petabyte data set. They started crawling in 2011. It has been 8 years now. It's giant. I don't even know how to download it. Recommended books. Some of the concepts here are based on these books. If you want to start with something, definitely start with the Introduction to Information Retrieval. Start reading it. It's pretty interesting stuff. So, any questions? Should.
You mentioned about stop words.
Stop words. Yeah.
So do you think it's still relevant today when you're actually doing neural networks and so they will indeed characters? The question was about stop words and if they are relevant today.
So if they make sense to still right now.
Yeah.
It's an interesting question. So as I said, as I showed you before, there is. Oops, sorry. Jeez. There's the possibility of doing this kind of search now, which is called semantic search, and you can do it also with documents. Problem is, we can't find a nice representation for text documents. There is research behind it right now, but the problem is to generate this feature vector coming out from a text. We can use, for example, Word2Vec, but they don't cluster. Similar documents don't really cluster together. So it's still an open question, but it's a very good question.
How can you do k-nearest neighbors on very large data sets?
On GPU,
Yeah.
first. You can do it on GPU.
Okay.
Second, there are specific data structures. I mean, these implementations are fast. I know k-nearest neighbor is usually considered slow. That's why you also do approximate, ANN, approximate nearest neighbor. These, for example, Annoy or Face, they are approximate nearest neighbor. They are not exactly k-nearest neighbor.
Thank you.
No, no worries. Don't be shy.
Coming back to the slide when you write when Codemotion is.
Uh-huh.
Yeah.
Stop me when you see it.
Is one of the first, I think.
Okay. Here?
No,
No.
no, I think it's one of the first. Early.
No, early there's...
Oh yeah, that
Oh,
one.
here.
That one.
Okay.
Yeah. This result is only ranked different, or it's the same result of a classic result of Google?
This is an actual answer, right? I'm asking when is Codemotion Rome?
Yeah.
And this guy is telling me, look, it's Friday. So it says, you know, it's a perfect result,
Okay.
right? And they know it. They don't even bother, like...
How they know it?
it's not, I'm feeling lucky. Like, give me the first result. Maybe it is, maybe it's not. This is actually their result. And how they know it? You can, whenever, so this can be based on, we don't know exactly, but this can be based on search. So it's among a knowledge graph is actually getting the first entity, and it's also telling you with what's the accuracy. So let's say that they get like 0.99. I can say, okay, you know what? This is probably the right answer. I'm just gonna throw it out.
Okay. It's not a different rank.
I mean, I haven't talked to Page and Brain recently, but I don't know how they implemented
Okay.
it. But typically, it's implemented
something
in
like
a...
this.
Yeah,
Okay, thank you.
no worries. Any other question? All right. Thank you. Thank you, everyone.